Hello everyone! In this lecture, we will cover security issues related to password-based authentication and session management. So, when discussing authentication, usernames and passwords are the most common method of authentication. However, one could say that it is also the least secure method of authentication that we have today, and this is indeed true. Password authentication is inherently insecure due to various reasons. First of all, people are not able to remember long passwords, so they choose weak passwords that may be guessed or brute forced by attackers. Password reuse is another concern, as users tend to reuse the same or very similar passwords across multiple websites. Hence, if a user's password is leaked from one website, it might be possible to access the user's account on other websites. Then, passwords are super vulnerable to phishing and social engineering attacks. Physical shoulder surfing attacks may be used to obtain the password while the user types it into the website. Key logging attacks can be used to obtain passwords if the user's operating system or keyboard is compromised. And so on. Today, there are other authentication methods that can be used to make password authentication more secure or even to completely replace it. For instance, we can use two-factor authentication, where a one-time code is sent over SMS, or an additional authenticator app is used to authorize logging into the account. There are single sign-on solutions provided by Facebook, Google, and other service providers that we can use to identify users on our website. These solutions typically use the OpenID Connect, OAuth, and SAML protocols for information exchange. Then there are the FIDO WebAuthn standards for secure public key authentication using physical tokens such as YubiKey. These tokens are slowly gaining some popularity. And in Estonia, we have government-issued secure authentication tools such as the ID card, mobile ID, and smart ID that can be used to establish the user's government-issued identity. This includes establishing their first name, last name, and a unique personal identification code. In most cases, however, websites do not need to know the legal identity of a user. But if possible, it would be good to replace password-based authentication with these type of authentication methods. But this might not always be feasible due to financial or scalability concerns. So, in this lecture, our focus will be on password-based authentication. But many of the concepts discussed will also apply when other types of authentication methods are used by a website. So stay tuned. And just to note, it is becoming increasingly common to see email addresses used as usernames for authentication, as this offers certain usability and security benefits. Anyhow, let's start by taking a look at the most basic password-based authentication scheme, which is actually called HTTP Basic Authentication. This scheme is part of the HTTP specification and is therefore supported by all major browsers. Here is how the authentication process looks like. When a browser tries to access a protected resource that requires authentication, the server returns status 401 unauthorized and an authenticate header with a string value describing the protected area. At this point, the browser will prompt the user to enter a username and password. Once the user enters their credentials, the browser resends the HTTP request, but with an authorization header that contains the base64 encoded username and password. So this base64 encoded value contains the username and password separated by a single colon. The server then decodes and verifies the submitted credentials and grants access to the resource. To avoid repeated authentication prompts, the browser remembers the credentials and includes them in all future requests to the server. Alternatively, to avoid the authentication prompt, the username and password can be passed in the URL. The use of such URLs is deprecated, but they are still supported by browsers. There are, however, a couple of limitations when using this authentication scheme. First, there is no built-in logout mechanism, as HTTP does not provide a method for the server to instruct the browser to log out the user. Users remain logged in until they close the browser or manually clear the cached credentials. One workaround is to redirect the user to this type of URL that contains incorrect credentials, but the side effect is that the browser will pop up the authentication prompt. Another limitation is that the website has no control over the user interface of the authentication dialog, so it cannot explain to the user what the authentication is required for. Historically, this realm string was displayed in the authentication prompt, but modern browsers no longer display it to avoid security risks associated with including untrusted text in security dialogs. By the way, this is how the Chrome browser used to display this text in the authentication prompt. As you can see, this is not the best practice for displaying untrusted text in security dialogs. Now, Firefox used to display it in a slightly safer manner, as it writes "the site says," helping the user to recognize that this text comes from the website. Anyhow, so the benefit of basic authentication is that it provides the simplest method for implementing password-based access control. As you can see, this does not require the use of cookies, session identifiers, or login pages, so this can be easily enforced in the web server configuration without the need to implement complex logic in the web application. The solution is basic, but it avoids the complexity of managing authentication sessions. While modern websites are not using this authentication method, it is commonly used in embedded systems such as home routers and IP cameras. Basic authentication is also used by HTTP proxies, with the only difference being in the header names and the status code. This distinction is required to separate proxy authentication from web resource authentication. So that's about basic authentication. Let's move on to discuss the most basic attack against password-based authentication, which is the password brute force attack. A password brute force attack or password guessing attack occurs when an attacker tries to guess a victim's password by trying to log in into a website with various passwords. This can be a dictionary attack where the attacker tries the most popular passwords, or the attacker may know the victim's password from another website and try different variations of that password in hopes of guessing the correct one. These attacks are a problem not only because the attacker may succeed in guessing the correct password, but also because they can lead to a denial of service condition on the server if the attacker uses many parallel processes to send these requests. Therefore, it is in our best interest to implement various countermeasures to demotivate the attacker from executing these type of attacks against our website. So, as for countermeasures, the most straightforward approach is to implement a logout policy where after, say, 5 failed login attempts, the user's account is temporarily locked. Here is an example message saying that your account has reached the maximum number of failed login attempts and has been temporarily locked. Please try again later or reset your password. At this point, the legitimate user may choose to reset their password instead of waiting, while the attacker is delayed for a specific amount of time. Another variation is to introduce progressive delays. For example, after the first 5 failed login attempts, introduce a 15-minute delay. After the next 5 failed attempts, add a 30-minute delay, then 1 hour, 2 hours, and so on. This would make the attack slower and slower with each set of attempts. In addition, after, say, 3 failed login attempts, the website could introduce a CAPTCHA to prevent automated password guessing attacks. And this is also where more general bot detection techniques can be applied. This can be further extended by taking into account the browser's past interactions with the website, applying IP reputation statistics, and so on. So here it is useful to apply risk-based adjustments to the policy. For instance, if a login attempt is made from an unrecognized browser, the website can enforce very strict rate limiting or even require two-factor authentication. While if the user has previously logged in successfully from the same browser or IP address, the policy can be relaxed with less strict rate limiting. Anyhow, the last and perhaps the most effective countermeasure against brute forcing is requiring strong passwords for user accounts. In most cases, this will demotivate the attacker because if the attacker knows that the website does not accept weak passwords, it no longer makes sense to try dictionary attacks using weak passwords. However, this will not help if the attacker suspects what could be the victim's password and only needs to try different variations of it. This is where these lockout policies and bot detection measures can still be of great help. The multi-user brute force attack, also known as password spraying or reverse brute force attack, is an interesting variation of the attack where instead of trying many different passwords for a specific username, the attacker tries one password against many usernames. So this is not a targeted attack. Here the attacker is looking to compromise any account with a specific, potentially weak password. And this attack is often overlooked because lockout policies typically focus on the account, tracking how many failed login attempts the account has received, rather than how many failed login attempts the attacker has made. Here is a good example from Swedbank, which many years ago used password-based authentication for online banking and was vulnerable to a multi-user brute force attack. The first weakness was that usernames were fully predictable because they were assigned as incremental numbers. This made it trivial for an attacker to go through each username. Another weakness was that the bank did not enforce any decent password strength requirements. As a result, the attacker tried the password 123456, and it turned out that 5,000 bank customers used such a weak password to protect their accounts. Allegedly, the brute force attack ran undetected for 10 days, which indicates that there was no monitoring in place to detect such multi-user brute force attacks. But the question is, how can we detect such a brute force attack? So here we need to count how many failed login attempts the attacker made. The limitation here is that the IP address is the only identifier that we can use to identify the attacker. So we can implement some IP address-based rate limiting. This is not perfect as the attacker can change the IP address, but obtaining a unique IP address for each request may be too costly for the attacker, so this may still work in practice. And then we can implement more advanced monitoring to detect sudden increase in login failures, and then determine what specific measures to apply when such an attack is detected. But first of all, this risk should be mitigated by enforcing decent password strength requirements. Let's take a look at the password strength requirements and the best practice in this area. To protect users from choosing too simple and guessable passwords, a website should enforce some reasonable requirements for password strength. A website should enforce a minimum password length, with 8 characters being the bare minimum. The website should also enforce a maximum password length to prevent some denial of service attacks, but the requirement is that passwords of at least 64 characters should be accepted. Longer passwords should not be silently truncated. Instead, the user should be informed that the password is too long, as shown in this example from GitHub. The website should allow the use of all characters, including Unicode characters, so no character should be banned in a password. And the website should not enforce character composition requirements, meaning that users should not be required to include special characters such as a number, symbol, or uppercase letter in their passwords. This may surprise you because many popular websites do enforce such character composition requirements. Not enforcing such a composition is a relatively new approach and somewhat controversial. The thing is that research shows that in practice, these complexity requirements do not help much because many users will simply capitalize the first letter and add some number or special character at the end. On the other hand, if we do not enforce any complexity requirements, how can we ensure that users don't choose too simple passwords? The idea here is that instead of demanding users to add some special characters to their password, it is better to encourage them to create longer passwords. For example, this is how GitHub has managed their password policy, requiring at least 15 characters or at least 8 characters, including a number and a lowercase letter. Another best practice is to prevent the use of the most common or compromised passwords. Again, an example from GitHub saying that password may be compromised. Password is in a list of passwords commonly used on other websites. Now the question is, where can we get such a list? Here is a publicly available list of the top million most common used passwords. So the application can check a candidate password against this list. And by the way, these are the top 100 most common passwords according to this dataset. Then there is also the Have I Been Pwned project, which contains a huge list of passwords that come from real data breaches. It is possible to enter a password here, and it will show how many times the password has been seen before. There is also an API that can be used to query this database in a privacy-preserving manner. Here's how it works. First, we have to hash the password using the SHA-1 hash function, then take the first 5 hex characters from the output and place them as a hash prefix into the API request. As a response, we will get the suffix of every hash that begins with the specified prefix, followed by a count of how many times it appears in the dataset. If our hash suffix is in the response, we know that the password has been compromised. We are using a hash here to prevent the server from learning our password and also to protect the server from disclosing the compromised passwords to us. This works because it is not possible to recover the password from the hash unless we know or can guess the corresponding input. It is also possible to download the entire hashed password database, but it is 20 gigabytes in size, so it may be quite challenging to use it in an offline mode. Anyway, so that's about preventing the use of common and compromised passwords. Another best practice is to not block the paste functionality for the password input field. The paste function is essential as it enables the use of long random passwords copied from a password manager. Perhaps you may have heard slogans stating that a password should never be written down. But considering how many different passwords a user is expected to manage these days, this is far from being a reasonable requirement, especially if we want these passwords to be long, strong, and entirely different from the ones used on other websites. As a positive side effect, copying of a password also mitigates keylogging attacks, as the user is not required to type the password in. Similarly, the password autofill functionality also should not be blocked. In fact, modern browsers will ignore this autocomplete directive on password fields, but there are workarounds how a website can still interfere with the autofill functionality. Regardless of the security risks, password managers do more good than harm, therefore their use should be encouraged. In fact, password autofill is very helpful in detecting phishing websites, because browsers automatically check the domain name of the website before filling in the password. So if a user is suddenly presented with a phishing website where the username and password are not pre-filled, this may alert the user about the suspicious website. And finally, passwords should not expire, meaning that websites should not enforce regular password changes. It has been found that such a practice does more harm than good, as it hurts usability without providing any tangible security benefit. So that's about the password strength requirements. Let's talk about secure password storage, which should include password hashing. A universally accepted requirement is that applications must never store plaintext passwords, because passwords are a very sensitive piece of data that should be protected on the server side, even from the server itself. Well, at least to the extent possible. Now, consider the following piece of PHP code that protects access to the admin interface. What we do here is that we check the submitted password against the hard-coded plaintext password, and if they match, we let the admin in. There's really nothing too wrong with this code, as the password here appears to be random and non-guessable. The problem with using such a plaintext password here is that if an attacker, by whatever means, gains access to this application code, the attacker gets the password and can log into the admin interface of the website. And this is where password hashing can help us. Now, consider this improved PHP code here. What we do here is that we hash the submitted password and compare the resulting hash to this hard hash value here. And if they match, we let the user in. Basically, we have achieved the same result, but now our code does not contain the sensitive admin password. Yes, the attacker can see the hash of the admin password, but this does not help the attacker to learn the password and hence prevents the attacker from logging in. What the attacker could try to do is hash billions of different passwords until one produces this hash value. However, since the admin password is long random value, this type of password cracking attack will not yield any result for the attacker. So what we achieved with password hashing here is that the disclosure of this code does not leak the password. Here, of course, we are considering only an attacker with read-only access to the application code. If the attacker had read-write access, the attacker could modify this code to log the plaintext password that is received here in this post variable, or replace this hash value with another one for which the attacker knows the input password, thereby gaining access to the admin interface. Alternatively, the attacker could simply remove this authentication check from the code. But the moral here is that it is always good to harden our system also against less powerful attackers. In reality, typically it is quite difficult for an attacker to gain full control over the server. Usually, exploiting simple vulnerabilities gives the attacker only some limited capabilities, and therefore a defense-in-depth approach can save the day. Alright, so that's the idea behind password hashing. Now, if we assume that all our passwords are long random values, then this simple password hashing approach would be sufficient and we could end this topic here. However, the reality is that most users' passwords will not be long random values, and therefore these passwords will be susceptible to password cracking attacks, where an attacker tries hashing many different passwords until one produces a hash value that matches the hash value of the user's password. Therefore, we need to apply some additional password hashing techniques to better protect, at least to some extent, also such weaker passwords. The first thing we can do is to append a password-specific random salt value to the password before hashing it. Here is how it would look in PHP. So the idea is that before hashing the user's password, we append some random data to it and then store this random salt value in the database alongside the produced hash. When the user tries to log in, we fetch this salt value from the database, append it to the user's plaintext password, hash it, and compare the resulting hash to the one stored in the database. If they match, we let the user in. Now here you may ask, what have we achieved here by appending such a salt value to the password before hashing it? Does it provide any improvement considering that the salt value is stored alongside the hashed password and is therefore available to the attacker who has compromised the database? At first, it may seem that such a simple hack provides no benefit. However, it does. First of all, it makes the hashing procedure unique for each user, meaning that even if different users have the same password, their hash values will be different because a unique salt is appended for each user. If we did not add salt, then by seeing the same password hashes, the attacker could conclude that the users are using the same password. The attacker could then bribe one user to obtain the password and thereby gain access to the other user's account. You got the point, right? So what this does is it prevents disclosure of users with same passwords. What it also does is that it prevents multi-user password cracking attacks. If we did not add salt, then the attacker could run a password cracking attack against all hashes simultaneously. That is, after hashing a candidate password, the attacker could verify the produced hash against all hashes in the database. Now, because each user's password contains unique salt, the attacker must perform the computation for each user separately. And thereby it also prevents pre-computation or so-called rainbow table attacks. The thing is that there are pre-computed databases known as rainbow tables that contain hashes of the most popular passwords. By using rainbow tables, the attacker can look up a password by its hash value without the need to hash different passwords until a match is found. Here's how it works. First, the attacker computes hashes of various possible passwords, and then sorts them by their hash values. Since the hashes are now sorted, the attacker can very quickly locate the password that corresponds to a specific hash value. These tables are huge and take a lot of time to compute, but once the table is ready, any hash value of interest can be looked up in a matter of milliseconds. Here's an example of such a database that can be queried online. So, 2 hash values were submitted here. For one hash, the corresponding value was found, but not for the second hash. The reason is that the input value for the second hash corresponds to password 123 and an underscore at the end. And apparently, the hash for such a password was not pre-computed by the service. Now, as you can see, such pre-computed databases will not work for salted passwords, because when adding a salt, the password that has to be cracked turns from a weak plaintext password to a long password with random gibberish at the end. And of course, it is not possible to pre-compute a rainbow table for each possible salt value that a password could have. Therefore, for salted passwords, the use of rainbow tables will not help, and to crack the hash, the attacker will need to try hashing many different candidate passwords until the correct one is found. Now, the problem is that standard hash functions are extremely fast, allowing attackers to perform millions of attempts per second. To slow down these password cracking attacks, we can hash passwords using a deliberately slow hash function. There are hash functions that allow us to specify the number of iterations the hash function should perform, thereby slowing down the hash function by a specific factor. While this slows down the attacker, it will also slow down our server. We probably don't want to spend 10 seconds here when authenticating a user, but perhaps spending 1 second could be an acceptable trade-off. That, of course, also depends on how many users our website needs to authenticate in parallel. Now, all this password hashing may seem like a complicated thing to implement. However, PHP provides convenient functions that can take care of this. We can use the password hash function when the user initially sets the password. Here we pass the user's plaintext password. Here we specify the bcrypt algorithm for hashing, and here set a cost parameter for bcrypt, which controls how slow the hash calculation should be. Note that this number here specifies the cost factor, so by increasing this number, the slowdown grows exponentially. Now, this function will return a hash value in this format. As you can see, the hash value is only the last part of the string. Here it encodes the hash algorithm used, options like the cost factor, and the randomly generated salt value. We can store this entire string in the database, and then when we need to authenticate the user, we can call the password verify function by passing here the plaintext password received from the user, and here this hash string received from the database. Since the algorithm, cost factor, and salt are embedded within the hash string, we do not need to pass these parameters to the function, which is a neat way how to handle this. Now, anyhow, what is important to understand here is that even if we add this salt and we use a decent cost factor to slow down the hashing process, password cracking of weak passwords will still be possible. Yes, it will significantly slow down the attacker, as it will not be possible to crack all weak passwords at once. But if the attacker is targeting a specific user, the attacker can throw a lot of resources of paralyzing the cracking process, and sooner or later, the attacker will be able to recover the weak password. So these password hashing techniques are not really a solution for crackable passwords. An additional hardening measure that could be applied is to append an application-specific random pepper to the salted password. Here's how it could look in PHP. Essentially, we just append to the password an additional random value, which is hard-coded in the application code. Of course, we would also need to do the same thing here before storing the hash in the database. And this will prevent password cracking unless this pepper value is also compromised by the attacker. So the idea here is to store this pepper in the application code while the salt and hashed values are stored in the database. This way, the attacker would have to compromise both the database and the application code to make any use of the hashed password stored in the database. And again, this kind of hardening makes perfect sense because now it is not enough for the attacker to have read-only access to the database. The attacker must also have read-only access to the application code. We can go even further by storing and processing this pepper value in some hardware token connected to the server, but that might be overkill. Although this depends on how serious we are about the security of our password storage. Then, a website should provide a password recovery mechanism in case users forget their passwords. This feature is nowadays called password reset because for security reasons, users should not be able to recover their existing password, but rather should be able to set it to a new one. Years ago, answering security questions or so-called password hints was considered to be an acceptable practice. But today, it is deprecated because guessing the answers to users' security questions may be much easier than guessing a password. The best practice today is to employ a password reset mechanism where a unique password reset link is sent via email to a user. Once the user clicks on the link, the user can set a new password for their account. Here is an example of a password reset form. So once the user enters the email address and clicks on a reset password, the user should receive an email like this containing a link to set a new password. What is important to note here is that requesting a password reset link should not invalidate the user's current password, because otherwise it could be used to perform a denial of service against the user's account, as anyone could use this form to request a reset link for the user. Only after the user has clicked on the reset link and entered the new password, only then the password should be changed. You probably have seen a password reset mechanisms where a user is sent a temporary password that must be changed after its first use. However, such a mechanism is less secure because in this case, the user's password is changed before the user has confirmed that the password reset request was made by the user. Now, there are a couple of requirements that the password reset link must conform to. First, it must be one-time, meaning that it must be invalidated immediately after the user clicks on the link, so that nobody else can use the same link to change the password. Then, it should expire after a maximum of 1 hour. This is to reduce the risk that someone could later gain access to the user's email archive and use a non-expired reset link to access the user's account. And each new password reset request should invalidate the previous link, ensuring that only the latest password reset link remains active. Then, what is super important is that the link should include an unpredictable token, ensuring that it cannot be guessed by an attacker. So the randomness requirements here are similar to those for generating session IDs and other secret tokens. Now, what you should notice here is that this goes against the principle that sensitive data should not be included in a URL. The problem is that we cannot include an HTML form in an email to send this value via a POST request. Therefore, we have to use URL to transmit the secret token here. So this here is an exception to the rule of including secrets in a URL. And actually, here it is fully legitimate to make this exception because this is a one-time secret value. As soon as the user clicks on the link, this value no longer needs to be protected since any repeated use of it will be rejected by the server. So this is one of the main reasons why this token must be one-time. Anyhow, important recommendation is that the user should be notified about any password change. For example, as you can see it here. And this also applies to password changes made using the regular password change feature provided by the website. This is needed so that the user could react if the password change was not done by the user. And finally, the password reset functionality should be rate limited. Here we want to prevent an attack where the attacker floods the user's inbox with a large number of password reset emails. Now, what you should realize by now is that the security of a user's account is only as strong as the security of the email account used to register in the system. If an attacker gains access to the email account, the attacker can, as a rule, gain access to all accounts associated with that email address. And this means that our email address is our digital identity, and therefore choosing our email provider is a very important decision. Well, alright, these are the best practices for implementing password reset functionality. A user enumeration attack may be used to determine whether a user with a specific username or email address is registered with the service. The simplest attack involves entering the username of interest and some dummy password into a login form, submitting the form, and observing the response returned by the website. Here, the website turns out to be vulnerable as it discloses that the email address is not registered with the service. For email addresses where this error is not returned, the attacker can deduce that the corresponding user is registered with the service. This creates a privacy leak, especially if an email address is used as a username, in which case it is possible to uniquely identify the registered user. Therefore, in such cases, this may also result in a GDPR violation, unless users have provided their consent to allow the service to disclose such information to third parties. You can imagine that there might be some sensitive services for which users would not be happy if their usage of the service would leak to the public. And even if the service itself is not sensitive, by compiling a list of services where a user is registered, an attacker can generate a sensitive profile of the user and their interests. A user enumeration attack also enables multi-user brute force attacks, as it allows the attacker to compile a list of valid user accounts that can later be used in password brute force attacks. Actually, there are several attack vectors that an attacker could exploit to perform user enumeration. Login forms is the first vector, and to prevent this type of attack, the website must return a fixed error message such as invalid credentials without disclosing whether the username does not exist or the username exists but the password is incorrect. Password reset forms may also be vulnerable to this type of attack. For example, this form is vulnerable because it responds with an error when a password reset is requested for a non-existing user. Note that exploitation here will not be stealthy because if the user exists, the corresponding user will receive an unexpected email with a password reset link. So, if you receive such emails, it may well indicate that someone is conducting user enumeration attacks. Here, the fix is to always return a success message stating that if such an account exists, you will receive a password reset link shortly. This way, the attacker cannot determine whether password reset was performed, and therefore the account exists. Account registration forms may also be vulnerable, as shown in this example where the form reports that the submitted email is already in use. Here, the exploitation will also not be stealthy because if the user does not exist, the account will be created and the user will receive an unexpected account registration email. But this depends on how this form is implemented. If the form warns about an already registered email address before other checks are performed, then, for example, by not checking I agree to the terms of service, the attacker can successfully check whether the email address is registered without actually completing the registration process. Here, the fix is to simulate a successful account registration, stating that the activation email was sent to the specified email address. And the website can indeed send an email reminding the user that the user is already registered using that email address. This trick, however, will only work if the website uses an email address as the username. In case of arbitrary usernames, there is no way out other than asking the user to choose another available username. Therefore, when using arbitrary usernames, the website can only slow down user enumeration attacks by employing CAPTCHAs and other anti-bot measures. And finally, it is often overlooked that email change forms under account settings may also be used for user enumeration. Here, however, the attacker must first register an account with the service to exploit this vector. This form here is vulnerable as the website returns that an email address is already in use. This form may also be exploitable in a stealthy manner if the email is verified before performing other checks. So here, the attacker can enter an incorrect confirmation password and perform user enumeration without actually changing the account's email address to the one being tested. The fix here is to always return a success message stating that a confirmation email has been sent. And if the address is already used, then the service would send a notification rather than a confirmation email. So these are the most common attack vectors for executing this attack, each offering different levels of stealth to hide the attack from victims. Now, when implementing the mentioned countermeasures, we must not forget about side channels that an attacker could exploit to differentiate between account existence and non-existence. Response timing is the simplest one. Here, we need to ensure that the response time is not faster for a non-existing user account than for an existing one. So it may be useful to perform some dummy operations to conceal these timing differences. Subtly different responses returned by the website may also be used as a distinguisher. This could occur when the error messages visually appear the same, but upon inspecting the response in more detail, it may turn out that a different HTTP status code is returned, or the error message is formatted slightly differently. So all these subtle differences must be eliminated. And the last and perhaps most overlooked side channel is due to differences in brute force protection. For instance, if a user account is blocked after several incorrect password attempts, then the same approach must be simulated for non-existing user accounts as well. To summarize, implementing protection against user enumeration attacks requires additional effort, but needs to be done to protect the privacy of users. And for your information, there are tools available that can automatically check which websites a username is registered on. For example, this tool checks a username against a list of 400 popular websites. As you can see, here the check is trivial because users on these websites have public profiles containing their usernames. So in this case, preventing user enumeration attack is likely impossible and probably unnecessary. And of course, there is no guarantee that profiles with the same username belong to the same person. More interestingly would be to query by a registered email address. And this here is a tool that can do exactly that. And as you can see, there are quite a few popular websites that do not implement protection against user enumeration attacks. Actually, the list of affected popular websites is much larger, but here are only those where this check can be performed in a fully automated manner. There are many websites where this check is still possible, but it requires solving a CAPTCHA, for example. Anyhow, so that's all about user enumeration attack. Let's slightly change the topic, moving on to session management topics, and the session fixation attack is something you should be aware of. As its name implies, the attack allows an attacker to set the victim's session identifier in a value that is known to the attacker. The full attack usually goes like this. First, an attacker somehow forces the victim's browser to use the attacker's session ID for interaction with the target website. This session ID could be one given by the target website to the attacker's browser, and the session ID should correspond to a blank, unauthenticated user session. Next, the victim logs into the website using the attacker's session ID, and since the attacker knows the session ID, the attacker gains access to the victim's account on the website and can abuse it to the extent possible. As you can see, a very brilliant attack. The only tiny problem here is that the attacker first has to figure out how to force the victim's browser to use the attacker's session ID. So by this time, you should already know some attacks that could be used here. The most realistic attack for an attacker would be setting the session cookie from a compromised subdomain using the cookie tossing attack. This attack, however, will not work if the session cookie uses the host prefix in its name. The next scenario is setting the session cookie by exploiting an XSS vulnerability in the website, but this requires finding such a vulnerability in the target website first. Then the session cookie could be set via a header injection attack. This attack would work if the website allows arbitrary user input to be placed inside the HTTP response headers. Here is an example of vulnerable PHP code where untrusted user input is placed in response headers. Such vulnerabilities, however, are not that common in practice. Setting the session cookie via temporary physical access to the user's computer might also be a viable scenario. Here, however, you may argue that if the attacker gains physical access to the user's computer, the attacker could set up a more powerful backdoor instead. And this actually might be very true. And the last possible scenario would be passing the session ID via URL, such as shown here in this example. Perhaps 20 years ago, this method of transmitting session IDs was quite common among web applications. Today, this is considered a very insecure practice, and if you see any website that does this, then something is very wrong with the website. Now, the problem is that even if a website is not using this method for passing session IDs, it might be that the server's configuration accepts session IDs passed this way. For example, in PHP, the default is to use only cookies to transmit session IDs, and this has been the default for about 10 years or so. However, there might be different web frameworks that accept session IDs from URLs or post parameters. If that's the case, then it might be exploitable under certain conditions. Anyhow, the question here is how to mitigate this type of attack other than making sure that the attacker cannot use any of these methods to fixate a session ID in the victim's browser. And the answer is that the best practice to mitigate this risk is to regenerate the session ID after successful authentication. This will mitigate the attack because the new session ID set by the website will not be known to the attacker. The session ID that the attacker knows will still correspond to the unauthenticated session, and hence the attack will fail. Here's how we can do this in PHP. We use session start to get the current session ID from the user, and then, if the authentication is successful, we call session regenerate ID, which will create a new session ID, copy data from the old session to the new one, delete data stored in the old session, and will return to the user's browser a set cookie header with the new session ID in it. And then we can update the new session array by setting the authentication status. So this regeneration of the session ID after login is the best practice that all web applications should implement. If the website has a vulnerability that allows an attacker to fixate the session ID in the victim's browser, the session ID regeneration will not prevent the attacker from fixating the session ID to one that corresponds to the attacker's login session. But at least the attacker will not be able to exploit this attack to gain access to the victim's account. And note that session ID should be regenerated also after other significant pre-authenticated state changes are made. What is meant here is that there are websites that enable users to submit or upload data before they are authenticated. For example, users may be able to add items to their shopping cart or start filling out forms, with authentication being only the last step in the process. To prevent the attacker from accessing this type of information in the pre-authenticated phase, the session ID should be regenerated after each such activity performed by the user. Let's take a broader look at the session management topic and the related issues. The first question we might have here is how to handle multiple sessions. First, should concurrent sessions be allowed in the first place? The best approach would be to forbid concurrent sessions, meaning that when a new login is made, the existing user session is terminated immediately. This way, active users would more easily detect unauthorized access to their account. While this may be a good practice for very sensitive applications, there is a strong tendency today to allow multiple sessions, as users may have several devices from which they would like to use the application concurrently. Now, regardless of whether concurrent sessions are allowed, it may be a good idea to notify the user when a login from a new device is made. Here you can see how such an email notification could look. It is important to provide some context here. For instance, the IP address or geolocation of the IP address, as well as the operating system and browser used for the login. This will help the user to understand whether the login was made by the users themselves or by an attacker. But here you may ask, how can a website determine whether a login is made from a new device? Basically, there are two approaches. A cookie-based approach where the website sets a permanent cookie in the user browser, and if a new login is made from a browser that does not have this cookie, then a new device notification is triggered. The drawback of this approach is that this will trigger many false positives if the user is using private browsing mode, as no cookies are preserved after quitting the mode. In the user agent-based approach, changes in the user agent header are used to detect a login from a new browser or device. This approach provides a better user experience, but is less secure, as in a targeted attack, the attacker can relatively easily determine the user agent of the victim. Requiring two-factor authentication for the first login from a new device is also a good idea. Note that the second factor here can be implemented simply by requiring the user to prove access to the email account or phone number specified during the registration process. While simple, such a measure can save the day if the user's password is successfully guessed or leaked through whatever other means. Then, if concurrent sessions are allowed, it may be useful to provide an option on the website to end all active sessions. Here you can see an example of how this could be implemented. Now, what is very important but often overlooked is that a password change must regenerate the session ID of the current sessions and invalidate all other active sessions. The reason is that the user might have changed their password specifically to lock out an attacker who has hijacked the user session or learned the user's password. If other active sessions are not terminated, the attacker could maintain access to the user's account even though the password has been changed, and new logins from the attacker would not be possible anymore. So this is something that has to be kept in mind. And the last note is that the website should require reauthentication at least for password or email change and before performing account deletion. Preferably, reauthentication should be required for any major change affecting the user's account. This helps in cases of session hijacking and also when an attacker gains temporary physical access to a user's computer. For instance, if the user forgets to lock the screen or uses shared computer and forgets to log out from the website. When implementing the logout functionality, the most important requirement is that the logout process must destroy the server-side session data. This is how it could be done in PHP by overwriting the session array with an empty string. It is not enough to simply delete the session cookie on the client side, as this would have the user session active on the server side. If an attacker had somehow hijacked the user session, the attacker's access to the user's account would not be blocked even after the user has clicked the logout button to end the session. Then it is also good practice to delete client-side session data, especially if it contains personal information. When deleting cookies, it is important to do so correctly. Here is an example of a common mistake. So let's say a website sets a cookie like this. If the website tries to expire the cookie by its name, but forgets to specify the same attributes that were used when setting it, then this will not work, because the browser will consider it to be a different cookie due to its different scope. So the same domain and path attributes must be provided when expiring cookies, because cookies are identified by their name, domain, and path. Other attributes are not important here, as they do not identify the cookie but are only used to set its properties. In addition to cookies, there are also other types of client-side data that should be deleted. The clear site data header provides a convenient way to delete different types of client-side data. HTTP cache can be deleted, all cookies set by the site, and all types of DOM storage can be cleared by returning this header. For cookies, this will clear cookies for the entire site, including cookies set by subdomains. Removing all cookies may be too extreme, as this would also invalidate cookies associated with cookie consent prompts and remove cookies that the website uses to identify a non-browser end device. The cookies directive will also clear out HTTP basic authentication credentials, so it can be used to implement Logout for basic authentication with the side effect that it will also remove all cookies. Now, regarding the HTTP cache, it is best practice to disable caching of sensitive data in the first place. Web resources that should not be cached by the browser must be returned using the cache control no-store HTTP response header, as this will instruct the browser and also the reverse caching proxy if present not to cache the resource. In Firefox, the browser's cache can be inspected using the About Cache URL. This serves as a basic browser forensics tool for extracting browsing artifacts, and it also nicely demonstrates how much information is actually cached by the browser while we browse the web. Therefore, sensitive websites should opt out of having their resources cached by browsers. Now, if the user has opened the website in several tabs, it is a good idea to detect the logout in those tabs as well and force a reload of each tab. Here, the DOM local storage can be used to share information across same origin tabs. After the user performs logout, the active browser tab can store a flag using local storage. The local storage set item method will trigger the storage event, which other tabs can listen for, and then redirect the user to the login page. To summarize, these are the actions that a website can take when a user clicks on the logout button. The question here is how to terminate a login session when users do not click the logout button but simply close the browser window or tab. Here it depends on whether the website is using persistent or session cookies for implementing authentication sessions. Persistent cookies will remain even after the browser is closed, and thus, by closing the browser, the user will not be logged out. Therefore, persistent authentication cookies should be used only when the Remember Me or Stay Signed In option is specified. Here is an example of a website offering to remember the session for 30 days. This way, the user can choose whether to use a persistent session on the computer from which the user is logging in. Of course, using private browsing mode should be the preferred method for users who browse the web on shared computer, as this ensures that all client-side session data is destroyed after the private browsing window is closed. But for this to work, users have to be aware of private browsing mode and the benefits it provides. Anyhow, using the session lifetime for authentication cookies should be the default choice, as this ensures that cookies are removed when the browser is closed. Here, however, it is important to emphasize that session cookies are removed only when the entire browser instance is closed, meaning that closing a particular tab or browser window will not remove session cookies as long as at least one browser window belonging to the same browser instance remains open. There are several workarounds that a website can use to terminate the session after the page is closed. The first approach is to detect the page unloading by listening for the pages before unload event and then sending a request to the logout endpoint. This before unload event will be fired not only when the tab is closed, but also when the user navigates to another web page. Therefore, an additional check is needed to ensure that the logout is not invoked when the user navigates to another page within the same website. We are using navigators and beacon here because this method sends the request asynchronously without blocking the page's unload process. This is not guaranteed to work reliably when the entire browser instance is closed, but in that case, the session cookies will be cleared anyway, ensuring that the session cannot be resumed. Then a website can store the authentication token using the DOM session storage. Since the data in session storage is removed when the browser tab is closed or when the user navigates to another website, this would destroy the session on the client side, ensuring that it cannot be resumed. The drawback compared to using authentication cookies is that in this case, JavaScript would need to attach the token to all authenticated requests made by the web page, which should not be an issue for single-page applications. The last workaround is using short-lived sessions with heartbeat requests. Here, the idea is that while the page is open, the website's JavaScript sends periodic heartbeats to renew the session and keep the session alive. Once the page is closed, the heartbeats stop and the session expires. How quickly the session is terminated depends on the heartbeat period and may not work reliably if the user's internet connection is unstable. Another aspect is whether a website should enforce session expiration for open but inactive login sessions. So here, the inactivity timeout refers to the lack of user interaction with an open website. Whether to enforce expiration largely depends on the specific application and its target use case. Enforcing expiration is useful for web applications that are likely to be used on shared or public computers. For online banking applications, this is not just best practice, it is a legal requirement. In particular, the EU Payment Services Directive states that the maximum time without activity by the payer after being authenticated for accessing its payment account online shall not exceed 5 minutes. Now, on the other hand, asking the user to frequently re-authenticate without a good reason can lead to frustration, dissatisfaction, and angry users. There is also a connection between frequent re-authentication and the success of phishing attacks. If the user is trained to frequently re-authenticate, the user may not pay enough attention when some phishing website asks the user to re-authenticate. Anyhow, even if a website does not enforce inactivity timeouts and uses long permanent authentication sessions, it may still be a good practice to regenerate the session ID after a certain period and to invalidate sessions after, let's say, 30 days of inactivity. With this, we want to avoid an attack where an attacker obtains an old backup of the user's computer, extracts the session cookie, and gains access to the user's account years after the backup was made or after the user's computer was sold to the attacker. To summarize, as you can see, there are quite a few things that need to be kept in mind when implementing session management for a website. Anyhow, with this, we end the lecture. Good luck with the homework.